Hello everyone, my name is John Sebastian Shakarian, and today I will be walking through my final update on my O-REU project, Non-Intrusive Reduced Order Models for Multidimensional Systems. I would like to thank my mentors, Dr. Ragusa and Dr. Tano, for their continued support of my project and constant help. I would like to additionally acknowledge the support of the O-REU program for my research this summer. In this presentation, I'm going to delve into several facets of our problem: the key issues, modeling of the setup, and the results analysis of our reduced order model. So our objective in this project is to be able to compute a solution to a field given a quantifiable phase space variable and parametric values. In this slide, this is denoted by u, x, and mu respectively. Because parametric dependence is tricky to fully characterize, many expensive in both money and time, simulations are needed to quantify uncertainty or optimize a design. We're using a non-intrusive reduced order model known as sparse grid subspace learning, or SSL. To reduce computational complexity and to retain a high-fidelity solution, reduced order modeling is a great method. With sparse grids, fewer points are actually needed to fully characterize and interpolate between all facets of a solution. This type of model order reduction is called non-intrusive because access to commercial source code is not needed to build any part of the model. Here you can see a typical sparse grid subspace learning level for 2 and 3 parameters respectively. So on the top you see 2 parameters and on the bottom you see 3. This image does a really good job representing how each grid level, denoted by n at the top, is trained on a greater number of points than the grid of a previous level. So one of the reasons for using sparse grids is to help solve the curse of dimensionality. This is a mathematical issue involving characterizing high-dimensional spaces. So as you can see, as the number of dimensions, or unknown parameters, increases, the number of points needed to characterize that dimension increases with it at a rapid rate. However, notice that the sparse grid point increase, denoted by the red line, is not nearly as sharp as the full grid increase, denoted by the blue line. In fact, as the number of dimensions increases along the x-axis, the benefit or difference between the two lines increases with it. So the benefits for using sparse grids increase with the number of dimensions. The problem we will be utilizing the non-intrusive model for is being able to predict the photon flux coming out of radiotherapy accelerators. This type of dosage and flux needed on a patient-to-patient basis rapidly changes, and collimating the beam needs to be done on an accurate basis. So using current methods to fully model the system is both computationally and monetarily expensive. By using sparse grid subspace learning, we can greatly improve the accuracy and efficiency of current models, and optimize the design for radiotherapy accelerators in the future. The impact being that this could greatly improve the health of people who need radiotherapy treatments accurately done. So here you can see the full 3-dimensional model of the linear accelerator head developed in MCMP 6.2. In this model, an electron beam strikes a tiny cylindrical target just above the primary collimator. This creates a cascade of photons, which will be collimated by the primary collimator, the flattening filter below it, and then a series of 4 jaws further below. For this problem, the full order solution we are looking for characterizes this photon beam on a scoring plane below the accelerator. This solution is a function of phase space, flight direction, and energy of photons. In addition, the positioning in or out the jaws are relative to the plane represents our parametric values for this problem, and by utilizing Tasmanian, which is a software in Python, we can find the relative parametric values that the jaws need to be to develop the sparse grid model. We can then run these jaw positions in MCMP to obtain our photon values for each jaw position. Now, when MCMP calculations were being run, a very important computational issue emerged. Because the problem in MCMP was constantly calculating the physics of 2 particles, the photon and the electron, the computational time to run a single file was not reasonable. In order to fix this issue, the problem needed to be reduced to only a single particle type, the photon. So to get rid of the electron dependence, a smaller model was created utilizing the target cylinder and 10 million target electrons. The bottom of the cylinder was analyzed with a tally, which grouped the exiting photons based on their energy. The resulting energy distribution can be seen on screen here. And please note that the massive spike that you see is a result of pair production occurring at 0.511 MeV. This energy distribution was input into MCMP and a simplified source for the full order model, which did not contain electrons anymore. We just had photons. Directionally, all of these photons in the new source were said to emerge between 0 and 90 degrees with a uniform probability. With this source now simplified into a single particle type for our full model, all future problems ran at much greater speeds. With the MCMP input fully characterized, the reduced order model was able to be built based on the specified sparse grid training points. I would now like to discuss some of the testing results we have obtained from the 50 testing points that we randomly sampled. Now, the sparse grid reduced order model is tasked with interpolating these random points to produce an equivalent output. Whether or not the model can do this accurately determines whether or not the model was a success. So pictured here, you can see the exact output of MCMP plotted on a trisurface with a logarithmic scale for the tallies in the z-axis. On the x and y-axis are px and py values respectively, which are sparse grid's way to determine the outermost jaw position corresponding to px equal to 1, and the most closed jaw position corresponding to px or py equal to -1, 0 being halfway for each. Each surface represents a different point along the scoring plane, which you can see in the title for each subplot. We will now compare this solution to the reduced order model's interpolated solution. So pictured here are the results of the reduced order model's interpolated solution when set to a grid hierarchical level of n equals to 6. Please note that all plots are considering the same scoring plane location, and in general, all solutions are built in a similar fashion to their exact counterparts. But just how accurate are we talking about? Pictured here is the relative error in percent on the z-axis of each scoring plane point that was analyzed. As you can see, the max error across all 3 points analyzed was an outlier of about 7% error in the corner of the scoring plane. Across all points analyzed, the relative error generally stays below 5%, indicating very promising testing results. So with this success in mind, I would now like to showcase the importance of grid level and the correlation that it has to accurate results. Here you can see 2 separate rows containing different level grids. On the top, you see an n equals 5 grid, and on the bottom, an n equals 4. These grids were trained on less total points, obviously, than the n equals 6 grid, which has been showcased thus far. As you can see, as grid level is lowered, so too is the total accuracy of the results. An n equals 6 grid produced a maximum percent error of close to 7%, as previously discussed. However, the n equals 5 grid jumps up into double-digit percent error, which is not nearly as good. And the n equals 4 grid, which was trained on only 29 points, is even worse, with the max error close to 17.5% and the majority of all error being greater than 5. This result really showcases the importance of sparse grid level on the fidelity of one solution. So I would now like to touch up on some of the brief statistical data we obtained. Here you can see that for the most part, the minimum relative error stays around the same order of magnitude until you reach the level 5 and 6 grids where it changes a little bit. So this is due to the fact that the number of testing points actually exceeded the number of training points for the level 3 and 4 grids. As you can see, 50 points were tested, and for the level 3 grid, only 13 points were used to train the model, and for the level 4 grid, only 29 were used. So this explains why those minimum relative error percentages were a little bit higher than for the level 5 and 6 grids. So I would now like to touch briefly on a current issue we're having with the model. So the output from MCMP is yielding mostly good statistics. However, upon deeper inspection into output files, some issues were found. 1 out of every 7 or so MCMP output files contain statistics with high degrees of error and tally values corresponding to photon fluxes of 0. And due to the underlying impossibility of this outcome, more work remains to be done in MCMP to determine the origin of this error and obtain even better statistics for the future. So in conclusion, the results of the reduced order model we created to predict photon flux look incredibly promising. When the model is fed correct statistical data and trained to a sufficiently high grid hierarchy, such as an n equals 5 or n equals 6 grid, it produces results with less than 5% relative error across the board. And while some issues persist with the MCMP modeling, the results here showcase the power of non-intrusive reduced order modeling, and will hopefully be used to improve existing technologies for the future. I would once again like to thank my mentors for their constant support and help, and would like to thank the O-REU program for giving me this opportunity to conduct this research. If you have any questions about my project, please do not hesitate to comment below. Thanks, and gig 'em.